as Dominic had before, is we can do model coupling with a fairly simple set of functions. That's going to be the basic model interface. So I'm talking today with my colleagues Eric and Greg. They are actual geoscientists, and we are a part of an organization called CSDMS. And so I'd like to talk just a moment about CSDMS because it has some important context for what I'd like to talk about today. And there we go. All right, so I'm trying hard not to read my slides. All right, so CSDMS is a group of scientists who do Earth surface processes modeling. So the ologies that we cover here are things like geology, hydrology, lithology, glaciology. All right, so it's a quite broad and diverse set of disciplines. And these people are gathered together. We do things like modeling of processes. We have a community, and we also do a lot of education. You can see our website there as well. As a little secondary feature of CSDMS, even though the science is the first thing, we're also big on promoting open source software. This is something that didn't quite exist in this community as of like 10 or 15 years ago. So it's kind of undergoing a bit of a sea change, a bit of a revolution, if you will. We're also into things like best practices. So Cyrus mentioned, for example, the FAIR principles. These are things that we teach a lot of grad students coming up now within our community. All right, so I highlighted model coupling because this is kind of this is our special sauce. This is why NSF likes to fund us. And I want to draw a little distinction between like what Deepak was talking about and like what William was talking about. Whereas they had to deal with a lot of problems that are global in scale, we tend to deal with more local problems and more local modeling problems. And so we don't run into the same problems necessarily as what Deepak described, for example, with the large data sets, and what William described with like the speed of doing the processing. So this informs a little bit about where we're coming from with CSDMS and where we're coming from with model coupling. All right, so how do we do the model coupling? Well, the first aspect of this is the basic model interface. All right, so again, the basic model interface is just a set of functions that we apply to a model. I'm trying, again, hard not to look at my slide, but I also enjoy this because I've been thinking about trying to find a different one-sentence explanation for how we can do the basic model interface. And so I asked this on our forum last week, and a bunch of our colleagues responded, and we kind of formulated an answer together. So I enjoyed that. That was kind of fun. All right, so the basic model interface. Why? Why might this be useful to people? All right, so this is my wife's car. She lets me drive it. Actually, my wife has 2 cars. I have 0 cars. This is one of them. She lets me drive this one. So it's a 2013 Subaru Outback. If I get into the Subaru, I sit down in the driver's seat. There's a steering wheel. I can control where the car's going. There's an accelerator pedal. I can go fast. There's a brake pedal. I can stop it. There's a speedometer. I can figure out how fast I'm going. All right, so there are controls in this automobile. Now, if I had to move a sofa, I could go to Home Depot, for example, and rent a truck. And I bet that if I got into that truck, I would have the same set of controls. I would know how to operate it. I may never have seen that truck before, but I know that I would have a steering wheel, an accelerator pedal, and a speedometer. So I've benefited by some standardization in automobiles. Wouldn't it be nice if numerical models had this? So that rather than having to learn how to run, Wharf Hydro versus Delft 3D, for example, if we had a standardized interface for how models work. And this is what we're trying to solve with the basic model interface. All right, so I have some design principles. These are things that we had tried to adhere to when writing a BMI. There's a lot of words here. I'll try not to go through all of these, but I'll probably try to cover many of them. So the BMI is language agnostic. It doesn't matter what programming language you use. We can write a BMI for it. BMI is self-describing. These functions have nice names that you can see across languages. When implementing a BMI, we use basic data types in the languages and use standard language libraries. We want the BMI to be easy to implement by a coder, because we're asking people for something. If you wrote a model, for example, as a graduate student, we're asking you to do extra work, extra credit, by adding on BMI functions. So we want it to be easy for the implementer, usually at the cost for someone trying to use a BMI. As a riff on that, we think of BMIs being for machines. Maybe not as easy for people to use, but easier for machines to use. I love the Popeye principle, so I am what I am. All right, so BMIs just describe themselves. They don't have to describe other things, other libraries. There's also the Hollywood principle. I didn't put this here, but the Hollywood principle is, don't call me, I'll call you. So BMI only responds when it's addressed. It's not advertising itself. It's not broadcasting itself. BMI models, for example, are used in a framework, and we leave tasks for the framework. It's not intended for every model. Not every model can be BMI'd. And it's for model coupling, but not necessarily model to model coupling. We can also do data to model coupling. We can think of data sets as a model. Like I think of a netcdf file, for example. Individual slices in time would represent individual updates to a model, for example. BMI does not inject itself into a model, so it's independent. You can still run the model without the BMI. The BMI currently, by name, is minimal, but it's open to extensions. That's actually a current topic of work. Right, so where can you find more information about the basic model interface? We have some documentation, and I'm really proud of our documentation. I think it works really well. People have been able to add BMIs to their models without coming to me and Eric and Greg and asking, well, how do I do this? So they've been able to go just from the documentation. We also have a fairly recent paper, this is 2020, where we describe the current version of the BMI. We also have specifications or mappings and examples. So the BMI itself is abstract. We just list function names and what the inputs and outputs should be. We've taken this abstract BMI and made it slightly more concrete in that we've set mappings for different languages. So you can see common languages that are used within our set of disciplines. I should also mention that the community has made mappings in Julia, JavaScript, and Rust as well. These are the ones that we work on in-house. Each of these has a repository and an example as well. The examples were kind of fun to make. We tried to make all the examples of using basically the same models, like a two-dimensional heat equation solution, Dirichlet boundary conditions, a uniform rectilinear grid, 0 with a spike at somewhere in the domain. So it's kind of fun to implement the same model across different languages. The implementation, again, this is the hard part to sell to people because it takes a little bit of work. So there are about 30 functions. They fall into different categories, like controlling how the model runs, initializing, finalizing the model, getting information about variables, doing time stepping, getting values out from the model, setting values into the model. The nice thing is that not all functions need to be implemented. A lot of them are kind of trivial to write as well. So this is just a screen grab, obviously, from the documentation showing a list of the BMI functions. All right, so BMI is actually being used in the community, which is kind of exciting and gratifying, I guess. So I just want to show, I went to dimensions.ai to get the latest counts of references. The Hutton et al., that's the recent BMI paper. The Peckham et al. Papers where the concept of BMI and actually CSDMS were introduced, and so it's been around a little longer. And then Tucker et al. Like a kind of a review of CSDMS. It's a little more recent. One thing that was kind of fun is the Hutton et al. Paper. It made a comment that most of these citations are in the last couple of years, so it's getting more uptake, which is kind of fun and exciting. So BMI is being used in different places. So maybe the biggest thing, this is kind of cool, the NOAA Next Gen Modeling Framework is using the basic model interface as a foundational principle for all models that go into it. And so there's a recent paper where this is described. You can see other government agencies, other government institutions, as well as private companies are using the basic model interface as well. So it's getting some use. And as a matter of fact, it's getting more use than kind of Eric and I can handle. So for a long time, the basic model interface was just Eric and I talking and just thinking about what should go next. Considering it is getting some use, a few years ago, we wrote up some governance documents for the basic model interface. We based on the NumPy governments, which I thought was helpful. And so we have a council now with representatives actually from the institutions you saw on the last slide. And they help set and guide the development of the basic model interface with time. We also have institutional partners from these places as well. All right, so current work, we're looking at developing an extension framework. So right now, the basic model interface is, again, just these functions, but there are other things that we'd like to capture with the BMI that shouldn't go into the core of BMI. And so things like parallelism, which BMI doesn't support yet, would be one of them. Not all the models in our community are parallelized, and so we don't really need that. Geospatial data as well is another place. So places where it would be better as an extension rather than having people implement them. We are working, so under the guidance of the BMI Council, we are working towards a new release of BMI, a version 3 release. We're targeting that for the end of September 2027, which is basically when one of the current awards that we're on runs out. We're also going to have a journal article as well. My little diagram is just a class diagram showing how we could do a geospatial expansion in Fortran. Okay, so in summary, the BMI is a set of functions that are external to a model code. They're intended to be straightforward to implement. They're a pathway to model coupling. And importantly, they're open source and community governed. Learn more at our documentation. All right, so with that, thank you. Any questions? Dominic?
Does this work?
Oh, yeah. Thanks so much, Mark, for this. So could you perhaps say a little bit about how it works when you're working across languages? Like, what's the technologies involved in that?
That's a good question. So this is something that we kind of defer with BMI. So the basic model interface, we use it for models written in one of the languages that we support. If we want to have, for example, a C model talk to a Fortran model, for example, we leave that for the framework. So for example, at CSDMS, we have one such modeling framework. We call this the Python modeling toolkit. And so that includes basically ways for us to work across languages. We basically wrap models written in these languages in Python and then have them talk to each other in Python. So to answer your question directly, it's a little bit outside the scope of BMI. We handle that in the framework instead.
But then yeah.
Sorry.
Yeah, thank you. That makes a lot of sense. I don't know if this is working anymore. Yeah, I think that kind of relates to what Cyrus was saying earlier about, it's difficult to just say to someone, oh, you have to use this one language, but if we want to move towards these, like the fair playground, like having this way you can get things talking together, having something like the BMI is like a way of sort of, okay, you implement this interface, and then you can fit into a framework that then sort of Legos it together, I guess.
I mean, in a sense, to build on what Cyrus said, we're using Python as our orchestration language in our community.
Yeah. Great, thank you. Other questions? I'll bring the mic over to you.
Hi, thanks for the talk. I think I'm struggling a little bit to imagine. Let's say I'm a grad student and I want to hook up a couple of different models. I have my own. What is like an example case when I should say, yeah, I want to hook up into BMI and grab something else? Like how would I reason about that?
Sure. How about this? Let me give a little example. This is my sort of pad example, and let me know if this answers your question. So the way I envision this is that researcher A writes a model that transports sediment downstream in a river. Okay, so the output of that model is there's a sediment outflow, there's a discharge at the end. Researcher B, maybe at a different university, writes a model that creates a delta from sediment. All right, so these two models could be written in different languages, for example. But kind of what we do at CSDMS is we would provide the middle. So researcher A could put a BMI on their river model. Researcher B puts a BMI on their delta model. The output from the river model would be used as input for the delta model. And I want to be careful because just BMI alone is not sufficient. Again, this is where we need the framework that would allow the two BMI models to talk to each other to actually transfer the information. But having the BMI on each of the models is the first step in this process. And so maybe if I could take a step back and go a little further as well. This is something that was by design from CSDMS. The idea was that we would have all these people in CSDMS, in this community, everyone writes their own model, and then if they put a BMI on their model, then we could write a framework that would allow people to pick and choose models from different places, to assemble them into the framework to do more science with bigger models.
Yes, that makes a lot of sense, as opposed to like inlining a bunch of new PDEs and then doing the whole thing together.
Right, right on.
Thank you.
Yeah, thanks for your question.
So following on to that, I'm curious about kind of schemas and things like units of measure. Dominic talked about like when you define what output your model provides or what input it needs. How do you describe that ontology?
Yeah, that's a good question. So we actually have something called the CSDMS, and let me know if this answers your question, Cyrus. Sure. We have something called the CSDMS standard names, which are built on the CF conventions. And so when we ask someone to write a BMI, we ask them to basically tell us what variables they want to expose through the BMI. Those variables will have names that follow the standard names convention, so they can do semantic mediation across different models with different BMIs.
Uh-huh. Okay, so it's based on the CF conventions.
Right, yep.
And the core data structures are just like kind of different numeric formats?
Right, yep.
And vectors of those and things like that?
That's right.
Okay, great. Other questions?
Sorry, since we got a little bit more time. So how would you compare it to another approach, which would be using couplers like Oasis or MCT or something like that? Like, how does that compare in this kind of space? Because I think you could sort of see it as maybe trying to solve a similar problem, but in a really different way.
I don't know if I'm familiar with these technologies. I'm not sure if I have a good answer for you. Oh, yeah, shoot. I'm not sure I can give a good answer. Just in the sense that, yeah, this is another way. I mean, there's other ones in the US as well. We have like Nuopsy, for example, from NOAA. These are different approaches to solving a similar problem, I guess. This is the one that was homegrown within our community. And maybe the advantage, which is also maybe a disadvantage, is that it's pretty easy to work with and pretty easy to implement.
Yeah. No, I think that's a huge advantage. I wonder, I don't know if this is right, but I'll say it and see what you think. Like you said, the Hollywood principle is, let me get it right, don't call us, we'll call you.
That's right, yeah.
Maybe couplers is like the opposite of that. Like you have to talk to the coupler.
Right.
And so you have to know about the interface of the coupler. So it's like the inversion of that, perhaps.
Yeah, that seems to make sense. Again, I want to be a little careful because I'm not sure I can quite talk about that.
Yeah. Okay, thank you.
Oh, is that good? Okay. Oh.
I think some of those other tools that you're talking about, Dom, they inject themselves into the code. So the code becomes dependent on some of those other couplers. And we don't want that at all. We want it to be independent. So if you're using, say, our coupling framework and you decide it's crap, you can switch to something else. It's no problem. You haven't tied yourself to a particular framework.
So our issues about sort of packaging and reproducibility and dependency management, those are all part of the framework rather than the interface presented, that like this model needs a certain Fortran library in order to run.
Yeah. I'm trying to think. I would say tentatively yes. I haven't thought about that enough.
Yeah, that boundary between the two, I think, is an interesting place to do some
right.
thinking.
Yes, yeah.
Mm-hmm. Okay. So could you give us some, so you have a bunch of users now. What have you learned from getting it out other than that, you need governance?
Yeah. Well, we learned about the need for parallelization, for sure. That's something that was a bit of a roadblock.
Can you elaborate on that? Like what aspect of the BMI?
So for example, right. So for example, like Wharf Hydro is parallelized, as is Del 3D and ModFlow. All right, ModFlow and Wharf Hydro do similar or complementary, they tackle complementary problems in hydrology. And so having BMIs on both of these pretty big models was great, but it was currently limited because we can only do serial operations. And so it was cool that they could talk to each other through a BMI, but not cool that they couldn't be parallelized at all. So that's an example of one thing we've learned.
But let me make sure I understand here. So the models themselves, like if you think of the model as a function that takes input and produces output, in between those two, it could do whatever it wants. It can run in parallel on a GPU, whatever.
Right. Yeah.
You're saying there's something about the coupling where it's not fully run one model to completion and feed the output into another, that they're more streaming into each other?
Well, yeah, we would do times on time step. And so like basically sharing, passing values between the models at each time step.
Okay, so it's about the coupling.
Two-way coupling.
It's not just function composition. It's something about a distributed system with communication. That's okay. Yeah.
Right.
Interesting. Okay, great. Where are we?
I think it's a good time to break for lunch.
Okay, yeah, we got lunch coming up here, so we'll come back after lunch and have discussions like this, and looking forward to it.
Cool, thank you.
Thank you to our speakers.